Hello. In the second video, we solve examples to reinforce our method to solve for the exact solution of a first-order differential equation. Specifically, we are going to learn how to get those constants associated with the homogeneous and particular solutions. So we start with this example. We have a first-order differential equation and we have this initial condition. We can start by comparing that to the nominal form, which was k1 dy dt plus k naught y equals to f of t. And we know that the complete solution y of t has two components, a homogeneous part plus a particular part. And in the previous video, we derived a solution for the homogeneous part y h of t as k, a constant, e2 minus k naught and k1 over k1 t, where k naught and k1 are the coefficients of our differential equation. By comparison, you can see that k naught is equal to 2 and k1 is equal to 3, and as a result, our homogeneous solution is equal to k e minus 2 over 3 t, and k here is a constant that we need to solve for using the initial condition, as we're gonna see later. So now we have the proposed solution for the homogeneous part. For the particular part takes the same form as f of t. For this problem, f of t is equal to e minus t. So as a result, our proposed particular solution would be into this form a e minus t. Now we don't know this variable a, this constant a, and we need to solve for it. One way to solve for it is to plug in this proposed solution for yp into the differential equation and solve for it. So our differential equation is 3 dyp dt plus 2yp has to equal to e minus t. We substitute our proposed solution for yp into that equation and solve for a. So we have 3 derivative of yp is equal to minus a e minus t plus 2 a e minus t, and this has to equal the right hand side, which is f of t equals to e minus t. Now you can see that we have e minus t both sides, and the coefficient of e minus t on the left hand side is equal to negative 3a plus 2, and on the right hand side the coefficient of e minus t is simply 1. For this equation to hold, the coefficient of e minus t in both sides should be the same, so we have to set minus 3a plus 2a, we have to set that to 1 so that the differential equation holds using our proposed particular solution. From here we can solve for a as negative 1. So now we solve for this constant associated with the particular solution, and our particular solution is equal to negative e minus t. Now we have a proposal for the two parts, homogeneous and particular. So the complete solution y of t is equal to the homogeneous part plus the particular part. You can see that we still here have unknown k, which is the constant associated with the homogeneous part. We solve for k using the initial condition. So the initial condition y of 0 equals to 5. So we plug t equal to 0 in our solution. So y of 0 using our solution is equal to k e minus 0 minus e minus 0, and this has to equal to 5. E minus 0 is 1. So from here we have k minus 1 equal to 5, and as a result k is equal to 6. So now we have our solution for k using the initial condition. Now we can complete our solution. Y of t is equal to k, which is 6, e minus 2 over 3 t minus e minus t. And this completes the solution for this first order differential equation. Now let's do another example. So in this example, we have a first order differential equation. Just to let you know that the independent variable can be any variable. So in the previous example, the independent variable was t. Here is an x. No worries. So now we are going to generate a solution y as a function of x. And you can see that the right hand side as constant. Okay. So comparing to the nominal form, we have k1 dy dx plus k naught y should equal to f of x, where x is our independent variable. Okay. The solution y of x would be of two components, a homogeneous component and a particular component. The homogeneous component, as we derived in the previous video, would be a constant times an exponential function whose exponent is minus k naught over k1 times the independent variable, which in our case the independent variable is x. By comparison, you can see that k naught is equal to 2, k1 is equal to 1. So the homogeneous solution is equal to k e minus 2x. Again, k is a constant and we are going to solve for it using the initial conditions later after we solve for the particular solution. Now we can propose the particular solution yp of x. Yp of x would be a scaled version of the function on the right hand side of the differential equation f of x that was a constant 50. So yp of x would be simply b naught, a constant. To solve for this b naught, we substitute our proposed solution into the differential equation. So the differential equation was dy dx plus 2y equals to 50. So now we have a proposal for yp. The derivative of yp is equal to 0 plus 2yp, so it's p naught, equal to 50. So from here we have p naught is equal to 25, and as a result, our particular solution yp of x is equal to simply 25. Now we have the two components, the particular solution and the homogeneous solution. We add them to get the exact solution. The exact solution, y of x, is equal to the homogeneous part, k e minus 2x, plus the particular part. Okay. Now we have this unknown. We solve it using the initial condition. So we have y of 0 equal to 40. So we plug every x equal to 0 in that equation and equate it to 40. So using our proposed complete solution, y of 0 equals to k e minus 0 plus 25, and this has to equal to 40. This is equal to 1. From there you can see that k is equal to 15, and as a result our complete solution y of x is equal to 15 e minus 2x plus 25, and this completes our solution. Thank you.